Hello and welcome back to Precalculus1, section 1.7, combining functions and also function composition. We talked about functions, defined functions, found domain of function, did graphing, and now we're going to take a look into algebra of functions. When you are looking at a function, you understand that the output is a number. So you might say f of 3 is 5 and g of 3 is 9. So now you have those 5 and 9 as answers. What can you do with the 5 and the 9? You can add them, subtract them, multiply, divide, square, and all these kind of things, which means that you have to be able to do the same with functions which created those 5 and 9. Let me give you an example of this. Say your function f of x is simply x plus 3. And say g of x is maybe x squared minus 1. So my question now is, how much is f of 2? Well, you will say 2 plus 3 is. Very good. And how much is g of 2? Very good. All right. So if I'm to ask you how much is f plus g of 2, you would say 8. It's common sense that 5 plus 3 is going to give you 8. The way you obtained that 8 was to compute 2 in f and compute 2 in g, and then whatever answers you got at the end, you add those two answers. So 5 plus 3 is 8. Or you can take the blue pill, right? Which is add functions first and then compute 2. So I can start this with f of x plus g of x, which is x plus 3 plus x squared minus 1, to give me x squared plus x plus 2. And then I can compute f plus g of 2, which would be 2 squared plus 2 and get 8. It doesn't matter if you compute a number in each function independently and then add results to get 8, or you work out algebra of adding functions together first and then plug 2 in the combined function. This line here, f of x plus g of x, is called combining functions, right? What we did is we combined two functions. We used algebra to put all of these things together, and then we came up with a new function. You will also see a verbiage which says making new functions out of old functions. And that's exactly what we did. We had these two functions, and we created the new function by adding, in this case, by adding the old ones. What can you do with functions? You can add them, you can subtract them, you can multiply them, you can divide them, provided that the one on the bottom is not 0. You can square a function, you can square root a function, right? And then I'm just going to write it here. This is the one that we are going to address later. You can plug one function into another function, which is called function composition, and that's going to have a whole piece of this lecture devoted to it. But let's first figure out some of these function combinations first. So I'm going to just pull some of the exercises. And everyone ready? It doesn't matter. Problem 36. F of x is equal to 6x squared minus x and then minus 1. g of x is equal to x minus 1. They want f plus g, f minus g, f times g, f over g, and all domains for these functions. So you are going to combine, using algebra, you're going to combine, obviously, addition, subtraction, FOILing, long division of polynomials, and then figure out what the domain for each one is. Let's go. I'm going to solve one of these in full so you can see the notation and the proper way to do it, because math, as any other foreign language you learn, you need to know how to spell, right? Which is the big portion of learning any mathematical concept. So I'm going to first say that I am working on f plus g of x. So in the parenthesis, I'm denoting that I'm adding f plus g and then of x, which means that I'm not computing it at any particular value yet. I will replace, now the meaning of this is f of x plus g of x separated, and I'm replacing this block by what it is, and then I will be replacing the second block by what it is. So I'm just swapping things. So now I'm going to swap f of x with 6x squared minus x minus 1 plus, which is the plus from the formula, and then x minus 1. So f plus g of x is going to be 6x squared, x's cancel, and then minus 2. This is what we have in the end. And then they say the domain, we know maybe that the domain of this function, you think about what type of numbers you are not allowed to plug in, and you realize that you are allowed to plug anything in. So domain is from negative infinity to positive infinity. You cannot put the inclusive brackets around infinities. So this is problem A, first one, solved in the, I would say, goriest detail, where you have proper notation, you have the answer presented, and then the... Now, there is another notation that you can adopt. It's this double bar R, and it means from negative infinity to positive infinity. This double bar R means set of all real numbers. So you can either, use this or you can use that. It means the same thing. It's a mathematical notation for all real numbers. You put two bars and then you just, right? So it's R with the double bar on the vertical. Great. I'll give you another few seconds to compute f minus g and the times and the, right. This is problem 36, and all these problems 31 through 41, they look the same. Actually, maybe even past that. Oh, I lied. All the way through 50. 31 through 50. They have different functions, but they all look the same in terms of what you're supposed to do. Yeah.
How do you see their if the domain is input and then the other side how do you see that?
Those are all of the values which you are allowed to plug in. Yes. So when you have a denominator, you know that you have to kick out all of the values which will make it 0. When you have square root, you know you have to kick out from the domain all of the numbers that will make negative under the radical. For polynomials, these guys, x squared and x cubed, all numbers are in the game. Because any number can be squared. Positive, negative, fraction, irrational, rational. Every number under the sun can be squared, multiplied by 6 and subtracted 2. So that's why it's negative infinity to positive infinity, just by looking at the shape of the problem. Yes. Sorry. The put the parenthesis over here so it didn't distribute it.
Why is it 3%?
Because the minus side will distribute and change that into a plus. Which, well, you kind of lucked out.
Yeah, because I took, when I subtracted, I said -2 minus, I'm sorry, -1 minus -1 is 0. So that's why I put that.
Yeah, but minus x minus x is minus 2x. Which is what you're missing.
Sorry?
Minus x is minus 2x. The ones are good.
I didn't get in time to complain about it. You know, you said, oh, I did the ones good. I said, yeah, you did. You did correct.
All right. So 6x squared minus x minus 1 minus, and now in parentheses, x minus 1, which gives us 6x squared minus 2x, and then -1 plus 1 cancels to 0. Again, domain, all the real numbers. Part C, f times g of x is going to be 6x squared minus x minus 1 times x minus 1. And now we do what? What do? Distribute FOIL. Great. So x times all of this is 6x cubed minus x squared minus x. And then -1 times each one of this is -6x squared plus x plus 1. I don't need parentheses. I don't know why I put the parentheses. We combine like terms. This is supposed to be cube over here. You guys hear it all? Yes. Yeah. G. If you try to do a long division here, you will see that it is not divisible evenly. So you will have to leave it like this. But what should we do for the domain? Yes. Equal to 0 what? Good. What do I get from there? And what is that? What we don't want. Very good. That's excellent. So how should I write the domain now? Am I allowed to put the brackets like this? No. What? Why? That means include. Exactly. And this means do not include. Nice. See? The devil is in the detail. Let's work on a slightly spicier example. Same rule, same question, everything same, different functions. F of x equals to 3x plus 1 over x squared minus 25, g of x equals 2, 2x minus 4 over x squared minus 25. This is problem 44. F plus g, F minus g, F times g, F divided by g.
No pressure, you're very keen, sir.
Right now.
And I forgot the denominator. Never mind.
Yes.
I didn't finish that sentence. I said, oh my. I almost said it again.
You're gonna mess up with the rules, I don't care. Whatever. No, I don't. I think this more than covers it. Yeah. And with this one, it's really no, it's not. What are you talking about? No. I don't want to use my brain.
As soon as he said it, it's like, yeah.
Watch your mouth. It's over. Alright, question. In any of your answers, did you have to cross out plus one? Okay, did you get this? The bottom, obviously, yeah. This one.
I'm not doing the name yet. I'm trying to get the problem.
Right. My friend just sent me something interesting that it's very related to, well, he sent it to a group chat, so I just picked it up there. I should send this to all of you. I know. Anyone wants to model these now over here? Huh. These are all the functions that you need in your Precalc1 and Precalc2. So I can send this, the email. Now it's a file, right? So yeah, it has all of the stuff that it definitely has the functions which you guys are considering: x squared, x cubed, 1 over x, root x. So the only one that's not here is the is the square root of x. You also know this one, which is the equation of the circle. You're supposed to know this from previous class. So, yeah, and then you have the trig ones, which are the next class. And you also have some of the transformations, right? You have the absolute x, right? The v shape this way, and then you have the negative absolute x going that way. So, and there you go. Make a flashcard out of that. Well, actually, I'm sending you this. You can make this the background of your phone. So you are reminded every time you're taking the awesome class. Actually, no, I'm going to post this in files. So, you know, if you're not interested in this, so I'm going to post this where the syllabus is. Oh.
I don't know what it is. So it is different.
All right. Let's take a look at these exercises. We have addition first. So f plus g of x is 3x plus 1 over x squared minus 25 plus 2x minus 4 over x squared minus 25. The common denominator is already there. In the numerator, we have 5x minus 3. Domain is broken at negative 5 and 5. Right? When you set up the equation and when you solve this equation from your algebra class, you get, right, you can factor out quadratic and get that x is 5 and x is negative 5. So domain is negative infinity to negative 5 union negative 5 to 5. It's not going to fit here. So domain negative infinity to negative 5 union a negative 5 to 5 union 5 to infinity. So we have two breaks in the domain because the denominator is 0 twice, and we have to exclude both of those values. So you see that the domain is from negative infinity to positive infinity with excluding negative 5 and 5. F minus g of x is 3x plus 1 over x squared minus 25 minus 2x minus 4 over x squared minus 25. So this is going to be x plus 5 over x squared minus 25. And this is where you have to be careful, because you know that the denominator breaks into x plus 5, x minus 5. That one cancels, right? It's still a break in the domain, even though if it cancels, it's the open circle. So the domain is still negative infinity and negative 5 union negative 5 to 5 union 5 to infinity. Later on in section 2.6, we are going to distinguish between these two cases. We will say that this one has two vertical asymptotes because these guys can't cancel. And over here where they do cancel, you will have one vertical asymptote and one open circle. So this idea will be built upon f times g of x is 3x plus 1 over x squared minus 25 times 2x minus 4 over x squared minus 25. We are going to FOIL x squared minus 25, everything squared in the denominator, and in the numerator we have 6x squared plus 2x minus 12x minus 4. So this is all equal to 6x squared minus 10x minus 4 divided by x squared minus 25 squared. We can factor out 2 on top to make it simpler, but we can't do much. That will be it. And probably one that you thought it would be the most difficult of all is turned out to be the easiest of all, right? Because you have 3x plus 1 over x squared minus 25 divided by 2x minus 4 over x squared minus 25. And when you consider, these guys cancel. So you are left with 3x plus 1 over 2x minus 4. So x cannot be 2, therefore negative infinity to 2, union 2 to infinity. Again, we set 2x minus 4 equal to 0, 2x is 4, x is 2. And that's it. Oh, I forgot the domain for this one. Again, the same domain as before, because it has the same structure in the denominator. Great. $4.50. I guess there will be a part 2 for this one, because there is no way that I can explain, teach the whole thing. I'm going to start, just write a few things, so don't close your notebooks yet. But we are going to actually do a lot more work on this next class. Guys, what follows is extremely important, especially for Calculus 1, when you are going to learn derivatives and you're going to have something called chain rule, which entirely rests on this. If you don't believe me, ask your SI instructor and she will confirm that. So function composition is extremely important and frequent. And what it entails is plug one function into another. That's what function composition is. It's the same like your bag. Your book has a function of some sort. For some of you, it's just to carry it around as weight for exercise, and others to open and read, right? Different function. But you have the function of the book, and you place that into your bag, which has a function to carry stuff. And that is your function composition, right? So function composition is where you plug one function into another. Notation for function composition is f, and then this circle, which is read composed with g of x. Also, f of g of x. You can clearly see that what used to be f of x is now f of g. That means that every x in function f is replaced by function g. I will write that. This notation here, I would say, clearly tells us that every x of f is replaced by g of x. Let's take a look at an example and call it a day. Much more on this next class, so we're going to dig deeper into these concepts. We take a look at, say, f of x is given as 3x minus square root of x plus 9, and then g of x is equal to x minus 6. To get function composition, f composed with g, which is also f of g of x, you are going to write the skeleton of f and then plug g for every x you had before. Observe that I copied the entire structure of function f, except I did not put any x's. Those x's are going to be replaced by g, so we have x minus 6 and x minus 6. You will follow through with algebra and clear up whatever you can in the next step, but the first step is the crucial step, where you realize that you are replacing every x with g. So we have 3x minus 18 minus square root of x minus 6. We can just cry about it. And then we have 3x minus 9 minus square root of x plus 6 as the final answer, because we plugged in this function into that function. In closing, I can also plug f into g, which turns the notation around. So g composed with f of x is g is the boss, and f gets plugged in. So g is the boss, and that is something minus 6. So that something, which is x, gets replaced by f. So I will plug f in here, which is 3x minus root x plus 9. Then you follow notation. You have 3x minus root x plus 3. Right, 9 minus 6 is 3. Observe that in all of these cases, we created a new function out of old functions, but I didn't add or subtract or multiply or divide those functions. What I did is plugged one function into another, and you can think of this as, plugging the book, which has a function, or your wallet that has a function, into the bag, which has a function. The function of the bag is separate than the function of the book, and you're able to plug the book into the bag. How many of these functions can we string together? As many as our application needs. You can take the book and plug that book into the bag, and then take that bag into the car, and then drive the car into the garage, and the garage is in the part of this big building, right? And the building is in this county, and then the county is, you see the idea? Each one of these layers that I'm adding on top have a different function. They're all plugged into each other, right? So next class we are going to discuss function composition in detail. We are also going to take a look at the difference quotient, and then some other functions that would, where we work with. So see you next class. All right, bye.